Hi, I'd like to introduce you to Lecture 2 in our course of Introduction to Computer Information Systems. In Topic 2, we're going to be talking about hardware. We provide an overview of what we mean by hardware, um, explain what are some of the components that make up a computer, and then also some information about what we talk about the commoditization of personal computers. Um, There's a couple videos here on YouTube. I'm not going to play them right now, but you can access them through the slide deck. Uh, we kind of they do a very nice job of kind of explaining what is a computer and describe the components around a computer. So you can actually look at those on your own. So from an overview perspective, there's a computer is a physical thing. Right? It's there are physical parts to it. There's different types of computers. So, if you look at the, kind of the whole family of computers that are out there, there's different types. So we've got our historical mainframe computers, and then, things that we're familiar with, desktops, laptops, mobile phones, tablet computers, e-readers. All of these different components make up or can be considered hardware. All right. Some special types of devices or different types of devices that are used with computers or used by computers. So storage devices, input output devices. You know, um, all of these different things really make up. They fall into this category of what we're calling hardware. And in addition, there's other things that also have you know, uh, microprocessors within them that really could be considered computer hardware. So the examples we see are things like cars. The amount of compute capacity inside your modern cars is very significant. You look at flat panel TVs have a tremendous amount of compute capability, able to get onto the internet and download and do updates and do all sorts of different kinds of things. So, computers, computer hardware is not necessarily just limited to computers. It actually kind of spans a wide range of devices, and that actual range continues to grow even as we speak. Fundamentally, when we talk about a computer, how does a computer work? So fundamentally, how a computer works is um, it's a bunch of switches, in its simplest, lowest level form. Um, and a switch can either be on or off, a 1 or a 0. All right, and this can be represented electronically. So basically, if you look at virtually every computer that's ever been made, going back to mainframes back in the 50s through your iPhone or your tablet, they all kind of do the same thing, and they're all based upon this idea of a digital 1 and a 0. All right. The fundamental unit. So the fundamental unit, when we talk around hardware, when we talk around systems, is an individual switch, or is called a bit. It stores either a 1 or a 0. And then what we do is we take these individual bits and we can group them together to make to represent things. We can represent numbers, we can represent letters, we can represent special characters. And in order to do that, you take a combination of zeros and ones. You take 8 zeros and 1. All combinations of 8 zeros and 1s actually can be used to represent all numbers and alphabetic characters. All right, so say for example, the number 1 in binary, with 8, assuming an 8-bit byte would be 00000001. A 2 would be 00000010. And so on and so forth. So if you think of base 2 versus base 10, we usually our arithmetic is base 10, which is represented by the digits 0 through 9. So, you go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you start over again 1, 0, 1, 1, 1, 2, and so on and so forth. Binary kind of works the same way. All right. So, but this idea of a bit and a byte is the fundamental, building block of computers. I mean, basically, every character you see on a screen, represented is a byte, represents 8 bits of data. So we talk around in a 64, say for example, everything in computing kind of revolves around numbers that are divisible by 8. So 8 bits in a byte, 32-bit. You'll hear things about 32-bit systems, 64-bit systems, which are all basically multiples of 8. All right, so if we kind of look at how many bytes are in a 64-bit processor, 64 divided by 8, so it's 8. All right. How many bits in a kilobit is, now kilobit is, or kilobyte is actually 1024, which makes it divisible. 1000 is not divisible by 8, but 1024 is. So 1024 is the is the size of a kilobyte. So it's 1024 bytes times 8, which is tells us how many bits are in a kilobyte. And this has actually been around since virtually every computer that's ever been made can be is basically uses this binary systems and basically uses electrical switches. Kind of as a sidebar here, the way this stuff has actually evolved has gotten faster and faster and smaller. We're actually starting to get to the point now where in quantum we're doing organizations are doing research like IBM and other organizations like that are doing research in quantum computing, which basically uses atoms, which is either a 1 or a 0. An atom, either charged or not charged, is the 1, represents the 1, 0. So you think about when you get down to that level of computing and the amount of information you could store when you're dealing with atoms is a kind of a mind-blowing thing. But that is something, that is an area of research. So what are the pieces of a computer? All right? So if you take your computer, I'm not suggesting you do this, but if you were to take your computer and kind of rip the cover off and take a look at it, you'll see a couple things on the inside. All right. So the brains of the computer is something we call a central processing unit, or a CPU. Basically, that is the component. So it looks like a big chip. It is a big chip. And what it does is it actually is the piece of the computer that actually will do the computations and execute instructions. All right. So the speed of a computer is measured in hertz. So the idea is the faster faster a processor can process, the more stuff it can do. So it kind of makes sense. But what we've seen over the history of computing is that processors have gotten faster and faster over time, and you can do more and more work. For the longest while, it was one processor, one chip, one CPU chip had one processor in it. So basically, everything was single-threaded. What we've seen now is this evolution of innovation by companies like Intel. What they've done is actually to increase the power of the chips. They've added multiple processors. So you'll hear the term dual core, quad core, so on and so forth. Which is really what will end up happening is the computer will will be able to run multiple instructions at the same time. Each processor kind of takes the work, it's broken up and distributes across in parallel across a whole bunch of different pieces, which significantly improves throughput. There's a concept, and you might hear this term Moore's law. So Moore's law goes back to, it's not really a law in is an immutable law of physics, but it was an idea put forth by Gordon Moore in 1965. And Gordon Moore was, I think he ended up as the head of Intel, but he made an observation that, you know, integrated systems and chips basically are, they really are containers of switches and transistors. And one of the things that Gordon Moore made the observation is that over every 24 months, the density of the transistors on an integrated circuit doubles. All right. So the idea is the net result is with more transistors, the more work you can do, the more switches, the more work you can do. So in effect, you start doubling capacity. So this is where you'll hear this, you know, the number, I think was originally like maybe 18 months, has been rounded up to like 24 months. So, basically over the course of 24 months, the amount of data, or excuse me, the capacity of CPUs will double. And this is actually, and it's interesting because basically he came up with this original observation back in 1965 time frame, and here we are in 2017, and it's actually been able to hold up there. It's not been in, there's no absolute guarantee on this stuff. A lot of the stuff, the multiple processors, the thing that really have enabled a lot of this stuff to move forward. But Moore's law has been in effect. It's still in effect. Obviously, a day will come when it will not be in effect. It will not be doubling every 24 months. But as of, that has been the case, and has really driven the compute world for the past 50 years. Another piece of the computer, if you were to pull it open, is something they call a motherboard, which is really just a circuit board that everything plugs into. So it provides, it's a home for all of the pieces, like for example the CPU, and it has the interconnections which connect all the different pieces together. So it can be used. It can add more components. So there's stuff that can be built. There's stuff that can be built into the motherboard, or you could actually plug things into it. So, the speed of the computer is to some degree driven by what they call the speed of the bus. The bus is the communication ports that link the CPU to the memory to all of the other things. So, one of the things that has happened as processors have gotten faster, the bus speed on the motherboard has gotten faster as well to make sure you can make sure it could keep up with the processor. All right. And then we'll see things like integrated video and sound components. Your modern computers are, your first computers, basically would beep. Modern computers are, multi-functional. Obviously can do data, can do video, can do sound, stereo sound. So it's the amount of sophistication on this stuff is very significant. So we look at like gaming computers and the way, the amount of horsepower it takes to run computer games and in terms of video is very significant. Right. Another component you'll see plugged onto a motherboard will be what we call random access memory. We call it memory, but probably the correct term is random access memory, RAM, which is working memory. So it's short-term memory. So this is plugs into the motherboard, and it communicates with the CPU. So it works. It basically has a electronic connection between the CPU and the memory. And what you want to think about with memory is think of like a vast array of post boxes. All right. If you go to the post office, you'll see all sorts of mailboxes where each one has an address. All right, and you can put something in each box. All right. So basically, that is really all memory is, except that you can. The amount of boxes, you start getting into like gigabytes of memory, becomes fantastical. But, in fact, basically it's an addressable box. The term random access memory really refers to the fact that you can get to any one of the addresses on a box. The address of a particular location in memory, you can access it directly. So it's used for short term. So the idea is that if you have the memory is if a program is running and there's stuff stored in the memory, it will stay in memory so long as you have electricity. As long as it's plugged in and the computer's running. You pull the plug on the computer, whatever in the random access memory goes away. All right. So you'll hear this term DIMM, dual inline memory modules, on motherboards. So that's really what most systems you see these days will have something, basically deliver. It usually comes in, you install it like in pairs, so you'll end up having like two chips, and basically memory shows as a couple chips. So basically, what you'll have is something like 16 gig of memory, which will be two 8 gig memory boards that get plugged into the computer, and it really drives the ability to run modern computing is really the amount of memory drives it. Modern, early systems had only very, very small amount of memory. It's only 640K in the original PCs. Now you've got multiple gigabytes of memory, which enables you to be able to run larger and larger and larger programs faster and faster. So and the difference between, say, for example, a storage, basically doing stuff through executing and accessing data that's in memory versus sort of a storage, is really it's infinitely faster to get that random access memory. But once again, you have to keep it running all the time. You have to keep power to it, or you will lose the contents. All right. So storage, when we talk around storage, this is, think of that as a longer term memory. So it's basically it's a magnetic disk mechanism. So you'll hear people talk about hard drives, and basically what a hard drive is basically it's a storage mechanism that will enable you to hold bits of information processed by a computer, both be able to write to it and be able to read from it. Right? So it's for longer term. We talk about hard drives. So hard drives is actually, you'll see it looks like a little block, little metal box, but what it actually is has a motor in it. The disks actually spin. So sometimes you can actually, if you put your ear on your computer, I can actually hear. If you put your hands on the disk when it's reading, you'll actually can hear or feel the disks actually spinning or moving inside. Solid state drives is really more of a modern, kind of a modern approach. Modern drives, basically, it's disk drives made up of what we call flash memory, which is similar to RAM, but it's basically it can hold data even then you don't have electricity, you don't have power running through it. So flash memory, it's lighter, faster, and more expensive. So, like, for example, you can buy a terabyte drive for about $50, and a solid state drive of the same size would be like $150. All right. And prices keep coming down, but so you're seeing kind of the price point continues to drop, and the capacity of what these things hold continues to increase. But the price differential between a hard drive and a solid state drive is still pretty significant. And then finally, what we have is like what we call removable media, which is actually the same kinds of things as, it does the same kind of function as a hard drive or a solid state drive, except that you can plug it into your machine and you can transfer data to it and then pull it out. So, what we see now is, the modern ways of doing it is using like USB flash drives and, basically, a little fob. But other types that kind of fall in this category: CDs, write once on a CD, or have rewritable CDs, or going back a ways, floppy disks, which are basically just another means of being able to do portable media. So the history of portable media, the first generations of PCs were not networked, had no network. So if you wanted to transfer information, what you would do is you would copy the information out to onto a floppy drive, and then bring it to somebody else's PC and plug it in and copy it onto that machine. So it's still around, still pretty useful. You see a lot of it, but it's just another form of storage. Talk about network connections. Basically, computers, first generations, much in the same way as we just indicated. First generation of PCs were not networked. Right? So it's been a more recent innovation. But basically, what it enables you to do, having a network connection enables you to be able to communicate to other devices or other machines or other networks. So we connect from we use a network connection to be able to connect from a laptop onto the internet and be able to access stuff on the internet, or be able to send email to other machines, or be able to do virtually a lot of stuff that we basically take for granted with computers. So the evolution of this has been from back first generation was things like modems, which were basically a device that enabled you to translate analog signals into digital signals and back again, which is basically what you need to do to electronic communications. And then that evolved into hardwired Ethernet cables, which is still pretty, I think it's still very much in use. And then much more recently, we see things around wireless networks, which is more the de facto standard these days. Input-output devices. It's once again on a motherboard. The ability to read and write data. Usually out to disk drives. So you either get data coming in or data going out. But those are ports on the motherboard that things plug into. A couple of the examples of this as we talk here, kind of the history of this stuff. First generation PCs had something called a serial port, very low speed, transfer of data. Kind of evolved into moving up what they call a USB, Universal Serial Bus, which is a standard that basically allows you to dynamically plug devices into a computer, and it'll kind of acknowledge it. And more recently, we've seen a lot more use of Bluetooth. So Bluetooth has actually been around a while. Really kind of jumped into the mainstream with personal phones and headsets and things like that. But you see around. Basically, it's a personal network, has a range of a couple feet. But basically, if you're running Bluetooth, you are your own personal area network. Wireless, of course. So we talk about servers. There's a class of computers. So basically, it's if you compare a server to, say, a desktop or a laptop. They're all computers. They all kind of work the same way. They have CPU, they have memory, they have I/O, they have motherboards. But those are actually more sophisticated. Computers, servers are designed to be higher end computing, which be able to run like enterprise type applications. So it's more resilient, more scalable. So the ability to run larger and larger bits of information, and more reliably. So we call higher grade, as we're talking about here, built from higher grade components. But it does have the same kinds of things. Like, for example, you'll see the motherboard on it. You'll see the CPU and all the supporting circuitry. So it doesn't differ on that. But what it will do is it will have like redundant power supplies. It has two power supplies, not one. We'll have like two network connections, not one. So on and so forth. All right. And then the other thing you'll see with servers are this multiple processors. So you see a lot of like higher end servers, which have, I think, dual was actually kind of an older concept now, but, multiple, like, 32 core, 64 core into a processor. with multiple processors in the being installed on an individual motherboard. So you got, you can imagine a lot of capability, a lot of processing power. A bit about networking, a couple things, so uh, there's really a couple different ways of how you architect storage. So, first level is what we call direct attached storage. So basically, you plug a storage device directly onto the motherboard. Either through a cable or some sort of connector, with no network connection. So, this was historically the way storage was connected in. So you had a computer, you plug your disk drives directly into it. Then you kind of saw kind of the evolution of this stuff. We call it like a network attack storage. So the idea is what you could do is you have more flexibility if it's not wired to an individual device. You can actually put it onto a network, and multiple systems can attach to it and share information. So that's just what we call network attack storage, or NAS. All right. Pretty big. I mean, still out there in a lot of organizations. Still a fairly significant market for NAS. Usually cheaper storage. It's network storage, but not necessarily super high performance, or but done with cheaper disks. Then we have what we call a storage area network. All right, so this is really kind of the mainstream of network storage. So very high end, very fast, a lot of redundancy, a lot of additional capabilities, a lot of smarts built into it, a lot of computing power is used in the storage area network. They all, but if you look at this, all three of these things basically do the same thing. It's a disk drive that a computer can write to, but where they differ is the speed, scalability, of the devices. So SANs are used, like for example, we use a SAN. We have a SAN environment in Campbell's that we run, their enterprise applications on, and we do some work with NAS. Your direct access storage is probably more for like what you see on your regular PCs. And this is just a chart kind of showing some of the comparisons of, between a direct attached NAS and SAN, so that you can see kind of under the complexity, capacities and complexities. You've got a fair, pretty significant amount of storage here, but obviously as you with NAS and in particular with SAN, you can put much larger petabytes of storage, which is very, very large. Also, you see kind of this comparison of complexity, relatively easy with DAS, a little bit more complicated with NAS, and pretty significant complexity associated with SANs. And this is just really like another display of what NAS looks like. So if you can imagine, it's just another, if we look at, we have a couple application server, print server, it's basically another server, but it serves up storage, as opposed to print services or application services. And just some more, little bit more detail on a NAS. It is a flexible, efficient global information access. It does simplify some stuff. There are some advantages with it. All right, but you don't see, for the most part, you'll see organizations for the most part these days are using SAN versus NAS. NAS has a kind of a role, but it's a lesser role than a SAN. A couple more, we're talking about different types of computing devices. Mobile computing, which is really kind of the modern form, kind of evolved out of laptops, but now we're seeing this idea of smartphones and tablets, the sophistication of smartphones, and as they've evolved. We're seeing integrated computing. So this idea of the term that gets used, and I think we'll probably be talking about this a little bit farther downstream, something called the Internet of Things. So basically every device that has a network connection in it, like for example a TV, TV has a lot of computing power in it, like to be able to get onto the internet and be able to do a fair amount of stuff. Some of the amazing things you get with TVs are you know, because you've got that much computing power into it. This evolution of, we talk around here, this commoditization. So basically what's happened is that as time has gone on, the first computers, the first personal computers, were fairly pricey. So they were a couple $1,000s. It was designed for, there were business devices. They were, kind of like one per department, and then kind of became one per desk. But as time has gone on, PCs have gotten, combinations of Moore's law plus, the way they've improved things with manufacturing. Basically machines have gotten faster and faster and faster and cheaper and cheaper and cheaper. So, but kind of an unexpected side effect of that was there was a, as PCs have continued to evolve and they become disposable items. So the byproduct of this is really this notion of you can't just throw a PC away because there's a lot of components in there, which with batteries and kind of like different things that are in the circuit boards really can be considered hazardous waste. So this whole, what you've seen is kind of this whole evolution of electronic waste and the need for it's the need for to be able to store, be able to deal with, as generations of computers get kind of tossed to the side, being able to deal with stuff and deal with it in an effective and efficient way. So we talked just a little bit about Internet of Things. So Internet of Things is basically you take every device, you give it a compute capability, you let it talk over the internet, and basically you've got a whole universe of new devices that are sitting on the internet. We'll probably talk about this a little bit downstream when we talk about cybersecurity and the implications of cybersecurity. So we will come back and see this again. So just some of the study questions. What is information systems hardware? It's really the circuitry and the components that make up a computer, or different types of computers. Moore's law, basically the observation that compute capacity basically doubles over a 2-year period, or 18-month to 24-month period, and it's been consistent over for probably the past 50 years. Personal computer is now a commodity. Is that as time has gone on, combinations of Moore's law plus the ability to make things cheaper and cheaper, and new generations coming out is PCs in a lot of ways have become kind of a disposable item. CPU is also known as the central processing unit. The bus on the computer is the communication device, is the communication that links memory to the CPU and to all of the different devices on for a computer. Two differences between RAM and hard disk is speed and capacity. So RAM is very, very fast, but not necessarily hold as much data. Disk drives are relatively slow, but you can hold many, many, many times more data. And advantages over SSDs over hard disks, is an advantage clearly is one of speed, speed and performance. Disadvantage would be obviously it's a more expensive item. Right? And that pretty much wraps up our discussion for Chapter 2.